Alright, is the chat box on? Chat box is on. Alright, Kon-Kazu lads, this is your electro student Vtuber, Natsuki Kazuya. So today will just be a simple stream, but with complicated topics. So we're gonna start studying some integral theorems today. But these integral theorems are actually like more of a continuation from our previous stream about double integrals and triple integrals. So the requirements for you to learn this is not just about double and triple integrals, but you guys should also know what line integrals and surface integrals are. So I'll try and cover that. I'll cover the line integrals and the surface integrals first, and then right after that we'll try and get some coherency on how should we differentiate on using the integral theorems. So okay, I'll try my best to get all of this down with any sense of understanding, because the topics today is pretty complicated, and the proof you need to also learn about how to actually use it in different kinds of applications. So okay, and I'm actually using the textbook I'm using is Calculus 4th edition. I mean, you guys can't actually see it at the moment, by Smith and Minton, yeah, Robert T. Smith and Roland B. Minton. So okay, as of right now, we'll start off with L-I-N-E. Integrals. So we'll try and put this down. And surface. That is an awful handwriting. Surface integrals. So okay, here are the two topics that we're going to cover for now, before we can actually cover the integral theorems. So okay, sorry, I think I've actually made a bit of a misleading title, kind of clickbait, but just roll with me for now with the basics of these integrals that we're going to learn today. So okay, what are line integrals? So line integrals are kind of like if you're going to integrate something, integrate some sort of line and try to find the mass of that line. Like for example, if you have some sort of a spring, so you use line integrals to actually find the mass of the spring. So okay, to try and get this down, I'll try and draw a random line here. So we'll change the color and set the outline to, let's say, orange. Okay, so we'll do this. Alright, so if you see the line, there would be a starting point and an ending point, and then there could also be sections of lines around here. So the entire line is actually known as C, and then these dots here are actually the sections of lines. So if we see this first section of lines, this would be C1, C2, and C3 with points, for example, let's say x1, y1, and z1, x2, y2, z2, and then x3, y3, z3, and then last point, the ending point, x4, y4, z4. So here are all the points, and these are the points that actually separate these lines, separate them into three different lines. So if you want to, so we define the line integral as the integration of, starting from, is it S or C? It's C. So apologies, C. Since this is a triple variable, so we should say this is f, x, y, z, and then we have to integrate with respect to ds. So this is actually defined by if we try and sum it up using a summation formula. So this would be the limit of from p approaching 0, then we'll do the summation of starting with I equals to 1 up until n, with defining the mass rho xi, yi, zi, and then we'll do delta s and also I. So if we multiply these two together and then we sum all of them up, and then we'll construct the limit. So we got, and then we'll get this line integral. So this is what the summation here is actually what they call the Riemann Sum, which is used in a lot of applications. So if you want to integrate this, like getting a pencil, to get my pencil, here's my eraser, so whoa, okay, no, that's not how you do it. How does this work? Let me see. Okay, I think I can just change to white, and we'll increase the line. Then we should cover this up. Okay, yeah. This is pretty weird. And why am I actually covering this? I should be covering this. So try that again. Alright. So now what you need, how you're going to integrate this entire the line integral. The first thing that you need to do is by changing the integral the ds over here. Oops. Oh wait, it's still black. Okay. So ds here it. So we need to do something called parameterization. So parameterization, we need to convert this ds into something like a magnitude, and then we change it to dt, because parameterization, you need to do this in terms of t, not t factorial, but t. So we need to if there is an equation of f x y z, we need to define them as xt. Is it xt? No, that's not xt. X prime t, which is if you remember from our last stream, is actually ds, if I remember correctly. No, not ds. Like if you remember the vector fields that we did before. The vector fields that we did, there is fx, fy, and fz. So x. So we'll do a square here. So this is actually like fx, but it's in terms of t. So xt y prime t squared plus z prime t squared. And then we have to change this in terms of dt. So therefore, this would be, just make things a bit shorter for ourselves. So we'll do like x from a to b. Now the f, since we're doing this in terms of t, would be xt yt. Dang it. We'll do that. We'll try that again. Instead of putting it here, we'll put it somewhere around here. So integrate with respect to a from a to b. It would be f xt yt zt. And then we have to rewrite this entire formula, the ds, into this equation. So we'll try and make this as small as possible. Xt squared plus y t squared plus t. There is still no room, but we'll deal with it and put a dt. So all of this will be in terms of t. So that is line integrals. So this is the basics that we would be covering inside the integral theorems later in the stream. So okay. So we'll go through line and surface integrals, the concepts first, but we'll also try and maybe do a bit of examples inside this textbook here. We'll do some examples after we define all of the theories here. So okay. let's go to surface integrals. Surface integrals, where are you? Right here. Okay. So right now, surface integrals are a bit different. So for example, if you have a line, we'll change the color to, this time we'll try blue. We have some sort of curve, but this not curve. This line is actually closed, and then it's moving in a clockwise direction. I mean, the direction doesn't really matter. This is the definition. And then here is some kind of solid. So what we're going to integrate is actually the surface over here. So this one, we'll label this as S. But if you want to like do the same for this line integrals here, we can actually split them into different pieces. Is that right? Okay, no, we don't really have to integrate surfaces like that. So okay, we'll say that this is the surface that we're going to integrate. So we'll use the Riemann sum again, and then we define this as, for example, as let's get my pencil, let's get my color again. G X Y Z. Well, this would also be ds. So that is that is the definition of the formula. But instead of the single integral from line integrals here, surface integrals, we use a double integral, but instead of C, we'll put them as S. So this would be the double integral from the surface S, g x y z, the function, ds. So if we equate it with the Riemann sum, it would be the limit, I hope this thing fits, limit p approaching 0, summation from n I equals to 1, then this would be rho xi yi. Sorry, my handwriting is slanting. God damn it. Oh dear. No. Wait, we need to move this canvas. We need to move the freaking canvas. Oh wait, we can. Okay, good. Okay, we'll try that again. So, okay. We'll grab a pencil. Oh, not again. Select. No, that's not how things work. Oh, okay. Okay, there we go. Grab it. Why does it move all the time? Okay. Okay. So, my goodness, this thing is getting wobbly. No, this is not working. Huh. I seriously wonder what's going on with my pencil. But I don't even want a straight line. Oh no. this? Okay, it's fine now. No, it's not fine, but it's what is actually going on here? Oh no. This is a big L. Give me a second, guys. I don't know what's wrong with my sketchpad right now. I'm using sketch.io at the moment. Why is it moving like that? Well, there we go. We have just suddenly made some sort of roller coaster. It's moving along with the why is it moving along with my freaking pen? It's getting shaky. Okay, hold on. Let me get a new one, I think. No, wait. Or maybe we'll wait. Alright, it's back. So I just refreshed the page. Okay, anyways, GX. Okay, where was I? Riemann Sum. So the limit, we'll do the limit of Riemann Sum, limit from P to 0. We'll do that. And I equals to 1. Rho xi yi zi delta si. So that is the Riemann sum for the surface integral. It's pretty similar to the line integrals, but different in terms of their overall shapes, I think, and the type of integrals used. So anyways, we'll take this off. But still, surface integrals still use the same concept like line integrals as well. So if we look at the textbook again, this seems complicated. So okay, in surface integrals, you also require something like a normal, I think, and you need to do some kind of cross product, and then you have to use the cross product, and then you need to find the magnitude as well. So 13.4 normal vector. 11.4. So, for example, if we do ds, and then we'll start with the delta s from si from the Riemann sum. And we'll do the magnitude of the cross product but it's also equals to the normal vector. But ds would be ni dot k. ds and okay, I'm getting confused at the moment. Or isn't this some sort of proof? I think this is just some sort of proof. So, okay. So this is ni. Need to find the magnitude of ni over the magnitude of n dot product k. Okay, where does the k come from? Hold on. AC. So we'll just say that nk, this the magnitude of n dot k equals to 1. But yeah, ds would also be dA because we're going to use double integrals. And because this this surface is over an area, so this is 1. So the only thing that we have is the magnitude of ni dA. So now, how should we define the magnitude of ni? Ni is the normal vector. The normal vector. So it has, and the normal vector, but we should also find the magnitude. This would be gx squared plus gy squared plus 1. And we'll put this up. We're using g because the function that we named here is g. Then we'll do from the region S. This time we'll turn it into a region R. G. Oh yeah, and surface integrals, despite it using like the same method as the line integral, surface integrals you don't have to do parameterization. So gx, gy, zz, then we'll do gx squared plus gy squared plus 1. dA. So that is the surface integral. So okay, still don't get it. So I don't get it either. But we're just evaluating this this surface integral so that this integral, like for example, this is the line, this is the perpendicular one, so this is like the normal line. So this is vi, this is ui. So we do a cross product of these two, and then we'll get the normal line. And we're going to do this like as if it was facing upwards, if I remember correctly. Is it? NDA. This is getting a bit complicated, so I guess if you have to like push me in, so oh right, so this is not Z, this is actually, oops, get the eraser, no wait, we'll stick with the pencil, convert to white, and we'll cover this up. So this shouldn't be Z, while this one would be fxy. So fxy, well technically if you do an equation that has x, y, z, you set the z into as the main equation, and then you let it in terms of x and y. So that's how you get the fxy. So even if you differentiate it, you would still get, it will still get 1. So wait, this one's not it. This is fxy. So that's how you do surface integrals. So if you guys could see the difference, let's make this a bit bigger so that you guys can see. Integrate region G, X, Y. I can hear birds chirping at my house, around my house. That's odd. So gx plus gy plus 1 will square, why am I squaring? A 1 squared, it will still be 1 squared, we'll make this thing quick, dA. So that's how you do, that is how you do the surface integral. So alright, let me get a sip of my water. Alright, so I'm back. So we'll do some exercises. So we'll get a new piece of paper. Color. Ooh, okay. Okay. So again, we'll do the same. We'll just do the same thing. This would be line integral. Whoops. This is surface integral. Surface integral. Today is pretty much something. Today is a pretty cold day, isn't it? And on the Saturday, it's really difficult for me to keep some nasal. I can actually feel my nose my nose is it's blocked today, and it's pretty freaking cold. Anyways, let's go back to the line integral. We'll do an exercise. Vector fields, no. So if you guys remember what I did on the previous stream, where in vector fields there is something that is related to conservation of vector fields, where let's erase this. Hope we can erase this properly now. Yes, we can. So we'll stick with the theory that the vector field F is equals to the gradient of that vector field. So if you remember from the last stream, if a vector field is conservative, why did I just put it here? Never mind. That if you do the gradient vector field to fx, fy, or if you have three variables, fx, fy, fz. So if you got it similar to the vector field, then that means it is conservative of path. So and then there is a lot of the terms that are similar to this conservation of vector fields. So if you do remember this, where is this? If you remember the fundamental theorems, if something like the F would be equals to 0. No, wait. Is it equal to 0? Huh. Okay, wait. Hold on. So let's not approach that first. Okay, so if you remember in vector fields again, that mx, xy, not mx, but it's not mx but my, xy, and then there's x, xy. So these two have to be similar in order for the line to actually be conservative or independent of path, or you can get the vector field would be equals to 0. So as well as if you differentiate like fx, xy, this would also be equals to fy, xy. Am I even making sense? No. Okay, definitely doesn't make sense. So take this eraser, erase that, erase that, and erase that. So n and m, n and m, n and m. So m would be equals to fx and n would be equals to fy. So since there are a lot of theorems in this, theorems. If the line integral is conservative, so we'll do something like c, f, and then dr. We can just do, if it's conservative, we can actually just convert this to f, x, y. So let's just put z in there, because we're doing a 3 variable. This would be x1, y1, z1, x2, y2, z2. So we do this. Like for example, let's say maybe x cubed. Oops, that's awful. X cubed plus y squared plus z. So we take these variables and minus with these variables. So that is the conservation of path for line integrals if they are independent of path. We just follow the same concept as vector fields, but we use this theorem to actually find the solution. So let's erase this. Let's grab a pencil. No, not that one. Wait. This is pretty hard to erase. Maybe the eraser is not high quality. So take that, take that, take that, take that. This is really hard to erase. Take it out, take it out, take it out, take it out. Do that. Okay, so let's get into the first exercise. Where is it? Okay, so let's just say we have this kind of helix, and this is a 3D curve. So we'll change the color to maybe some sort of pink. 1, 2, 3, 4. And that is how you do that. So we'll define this. If you use the right hand rule, this is x, this is y, and this is z. So these are defined by x equals to 2 cosine t, y equals to t, and z is equals to two sine t. So it's kind of like it kind of looks some sort of a spring because of the x and the y coordinates. So okay. So the first method to do this, we need to like differentiate this to cosine t x prime t. So if we differentiate this, differentiate cost will be minus sine, minus 2 sine t, y equals to t, and then differentiate that would be 1. Z equals to 2 sine t, z prime t equals to 2 cosine t. So okay, now we got that down. So since the line integral is the line of S F ds, line is actually C, not F, but it's ds. So ds would be minus 2 sine t. Oops, we haven't used the integral yet. Squared plus 1 plus 2 cosine t squared. So if you look at it, so ds would be dt. So let's see, 4 sine squared t plus 4 cos t plus 4 cos squared t plus 1. So this identity will be converted to sine squared t plus cos squared t will be equals to 1. No, sine squared t plus cos squared t is equals to 1. But there's 4 here, so we'll change this to 4 dt. So this would be square root 5 dt. So if we put in the formula, we should actually, oh, the region, I forgot the region. So 0 from t to 6 pi. So we'll do integrate c f ds will be equals to approaching 0 to 6 pi. And since we've already parameterized, or isn't there a function around here? Okay, so I forgot to define the function as well. So x, y, z. This would be 2y, but y is equals to t, so this would be 2t. 2t square root 5 dt. So now we can just take this out. 2 square root 5. So the t would be t squared over 2, 0 equal to 6 pi. So we'll take this 2 square root 5, but if we do t, would be 6 pi squared over 2. Okay, so we didn't get the exact values. So 6 would be, since this is 2, put this up. So 36 pi squared root 5. And that is the answer. So give me a second. Let me try and get an example for the surface integrals. Alright, so we should do this. Evaluate as z ds, but there's also a region where it's 2x plus y plus z equals to 2. So this is the region bound. The region bound, and it's lying in the first octave. So since we're just using we're using a double integral, we'll make a curve. We'll make a graph consisting of x, y, z. So since we're just going to do the region, z equals to 2 minus 2x minus y. Oh, okay. So we have the three variables here. So hold on. This is going to be bounded by the region. Bounded by the region. 2xy 2 lying in the first octave. Now, what was that again? The normal, yeah. So we can actually define the normal as n So taking from this equation, we use partial derivatives. 2, 1, 1. 2, 1, 1. And then we do the magnitude. So it will be 2 squared plus 1 squared plus 1 squared. This would be square root 6. So since this is ds, we need to change this to dA later on. So integrate s 3z square root 6 dA. So if we do this, z would change to 2 minus 2x minus y. Minus 2x minus y, so 3z square root 6. So we'll take that out. We'll do 2 minus 2x minus y. And then if we want to make the region bound, like for example this one, like this part here, we'll have to make z equal to 0, so that 2x plus y equals to 2. So we'll do the intercept here 2. And then we'll do the intercept here 1. So this will be our region. So if we do like an xy curve, xy, so 0, 1, here's 2, so 0 approaching 1, so this one would be y is equals to minus 2x plus 2. So this would be y approaching from 0 to 2x minus 2, or 2 minus 2x. So now we can actually take out these 3 square root 6 out. So we'll change this to dx dy, x approaching 1. So equate this, square root x dy, 0 approaching 2 minus 2x, 0 approaching 1. Was that right? So 2 minus 2x minus y dx dy square root 6. 2 minus 2x. Hold on, shouldn't it be the other way around, I think? So this one would be 1. Okay, let's undo that. 0 approaching 1. Okay, we'll take out all of that. We'll do this one more time. So 1 will have to be outside. So 0, 2 minus 2x. Minus 2x, so this would be 2 minus 2x plus y dy dx 3 square root 6 0 1. Now we integrate them. Now we integrate the inside. 2y minus 2xy minus y squared over 2. So 0, 2 minus 2x dx. So put this up. 3 square root 6. 3 square root 6. 0 to approaching 1. This would be, so let's just immediately multiply this. 4 minus 4x minus 2xy. But this is y, so 4x plus 4x squared minus 4x plus 4x squared. And then this one should be 4 minus 2 times 2 times x. 4x. So 4x. So we'll do in parentheses 4x squared over 2. Anything else? 3 square root 6. So this would be 2, this would be 2, this would also be 2. That doesn't look like 2, that looks more like a worm. So 0, 1 dx. 4 minus 4, 8x plus 4x squared minus 2 plus 2x minus 2x squared. So now we do that, and then we do that. We'll erase this up. Hold on, guys. Square root 6. So now, once we got that done. 0, 1, 2 minus 6x plus 2x squared dx. So I think we'll just integrate straight from my calculator. So 3 square root 6 integrate from 0 to 1. 2 minus 6 x plus 2 squared. So the answer is 703 something. Huh. 703. Oh, it's not, that's 7. Where did I go wrong exactly? 3 square root 6. This should be minus 1 over 3 equals to minus square root 6. I think there's an error somewhere, but I think we'll leave it out for now. So here we'll just put in we'll create a new one, and this time we're going to learn about theorems. So let me take another sip. Alright, let's fill this blank canvas with some new ideas. Alright lads, so if you guys see the thumbnail, so let's do some of this in integral theorems. So there are 3 theorems. We'll start with the simple one. Green's theorem. And then we have the Gauss theorem. Gauss theorem. And then we have the Stokes theorem. So, okay, I actually forgot what was I about to say about Green's theorem. Give me a second. So, okay, just remember that Green's theorem doesn't use a parameterization or anything. So Green's theorem uses something like, we use the concept of double integrals, but we're also using area application. Well, I guess there isn't any. But if you do remember just now that line integrals, they use like dx and dy as well. So Green's theorem, we do a line integral of mxy dx plus n xy dy. So the theorem will have to make a double integral of r, then we'll have to do the partial derivative, not like, is it this symbol? Yeah, it is this symbol. So yeah, dn dy, no wait, dx over dn dx, dm dy, and then we'll have to change that into dA. So Green's theorem is like, okay, if you remember just now, the line integrals, it has something like the function xy and then x1 y1 x2 y2, so comma that. So and then you minus these two. Well, that is for conservative, but in Green's you convert them into partial derivatives with n respect to x and m respect to y. So this one should be x, this one should be y. So yeah, that is how you get the Green's theorem. So okay, next would be the Gauss theorem. So Gauss theorem and Stokes theorem, both of them comes from the surface integral, but Gauss theorem and Stokes theorem are two. You have to differentiate them just by doing by two methods from the vector fields. So Gauss theorem you use divergence. You know the divergence if you do vectors and then make a dot product, that is the divergence. While Stokes theorem is related to the curl. So the curl, if you do a vector field, cross product, not that, yeah, cross product with another vector field, and then you do this. That is the main difference between Gauss theorem as well as Stokes theorem. Oh yeah, and depending on the question, you guys just use Gauss theorem is more towards triple integral, while Stokes theorem is a double integral. Oh yeah, Green's theorem just now is also a double integral. So okay, Gauss theorem. We need to convert this. So Gauss theorem comes from the surface integral. So F and ds with the surface here. So we'll do 1 to triple integral. With a solid here. So divergence is defined by div f, and the region would be in dv. So if you remember triple integrals last stream, we'll do instead of dA, it's actually dv. So that is the divergence theorem. So okay, next would be the Stokes curl theorem, the Stokes theorem. But Stokes theorem is coming from a line integral, if I remember correctly. So from the line integral, so we'll get an eraser. Oops, what just happened? We'll get the eraser, erase this. It's still really hard to use this. So let's just make a line here, line integral here. C F dr. We'll do that, double integral, then the curl theorem with F, no, not that F, but the vector field cross product with the F. So that is the curl. And then we have to put a normal vector here. And then we'll do ds. So that is the Green's theorem, this is the Gauss theorem, and that is the Stokes theorem. So that is the relation between these three streams, between these three theorems. So I believe we can actually do like a few exercises here. But I think as of now, I think I need to take a break first. I'll have to go to the toilet. Just give me a second. Alright, I'm back. So, okay. Do this again. So, okay. Now, what should we do next is we need to do some exercises. So, give me a second. Let's just make I think we'll make a new one. So let's start doing an exercise for Green's theorem first. So let's just make the formula Green's theorem, integrate the line of f dr would be d n dx minus d, no, not that d, oops, it should be like this, dm over dy dA. Is it dA? Is it really dA? It was dA just now, right? So yeah, I believe it is. So okay, we'll do the first example. We'll do the first example. We'll make things a bit harder for ourselves. Make a circle, 1, 1, and we'll do 3, 3, y, x. So here is the region. This is R. now we have to evaluate the line integral of the C 7y minus e to the power of sine x dx oops, no, that's the wrong question, my bad. Ex plus 6xy dx, that is the m plus ax square plus sine y cube. No, sine y squared. Okay, what's next? Oh wait, dy. So this one would be m xy, this would be n xy. So mxy would be equals to ex plus 6xy. But since this is dx, so we could read, oh yeah, there's a lot of things I forgot here. Okay, wait, before we do anything, this region right here is bounded between 1 and 3. So, and then this is a quarter circle with the radius between 1 and 3. So r 3 1. So r is between 1 and 3, and then this region is actually around at the first quadrant. So 0 theta, what was that again? Pi over 2. So pi over 2 is 90 degrees. Since pi is 180, 2 pi is 360, 2 pi is actually a full circle. So my, if we differentiate this would be 6x. So if you do partial differentiation, this would be 0, and then this one would, the y would be gone, so left with 6x. So n would be 8x squared plus sine y squared. Now we'll do nx. So this is x squared, so this would be 16x. So if we evaluate to the line integral, we need to convert this into a circle. No, we need to convert this into polar coordinates. But before that, we need to, so let's just say that x is equals to r cosine theta, y is equals to r sine theta. So this would be 16x minus 6x. This would be dA. This would be equals to, integrate respect to the region, 10x dA. So now we cannot use the rectangular coordinates since this is a circle. So we'll do from 0 to pi over 2. So we have to change this x. So from 0, no, this is radius. It's 1, 2, 3. 10 r cosine theta dA. No, wait, not dA. dr d theta. So big arrow here so that we can calculate the integrals here. Integrate from 0 to pi over 2, 1, 2, 3, 10 r cosine theta. So cos theta dr d theta equals to 0 to pi over 2. So this would be 5r squared cosine theta 1, 2, 3 d theta. Yeah, it's too small. Sorry about that. 0 to pi over 2. So we'll leave the cos theta aside. So this would be 5, 3 squared minus 5, 1. This would be d d theta. We're just using whatever space we have right now. So sorry about that. So 0 to pi over 2 cosine theta. So 5 and then 3 squared. 3 squared is 9. 9 times 5 is 45. 45 minus 5. So this would be 40 d theta. So 40 integrate cos. Integrate cos would be sine. 40 sine theta 0 approaching pi over 2. So the answer is 40 because sine pi over 2 is 1. This is equals to 0. So the answer is 40. Am I correct? Oh, dang it. No, it's not dr d theta, it's r dr d theta. So this one would be r squared, r cubed. So this isn't 5, 10r cubed over 3. So we gotta try that again. Dang it. So wait, we need to erase this. This time we'll use the pencil. We'll go for maximum here, like that. Just erase the whole damn thing. There we go. Go to white. Two. Alright. Apologies for the awful handwriting, but let's do it. So we'll try that again. Pi over 2. Take out cos theta from this. And then we'll do 10 3 cubed minus 3 minus 10 3. I hope bear with me with this. So 1, this is 1, not 4, and this is 3. So now we still need to use the calculator. So 10 3 cubed over 3. This would be meant as pi over 2 cos theta 90 minus 10 over 3. 90 minus answer. This would be 260 over 3. 260 over 3. But this time we'll integrate this. This time we'll just immediately integrate the cosine. So it would be sine theta. Sine theta approaching 0 to pi over 2. So the answer would be 260 over 3. And the answer is correct. So that is for Green's theorem. Let's try and do another exercise. So let's create a new one. Like that. La la la. Pa pa pa. Okay, next would be not the divergence theorem. Divergence theorem or Gaussian theorem, their name is just interchangeable, but I like to call it Gauss theorem. Okay, so if you remember the formula again, it uses the surface integral Fn ds s equals to the triple integral with a solid Q divergence F dv. So it's the triple integral, but it's also a some kind of solid. So you guys got that? Anyways, let's get an exercise from this. Oops, snapped my fingers there. Sorry about that. Okay, so here's one exercise. So we have a solid x, y, z. So this is a paraboloid. If you know what paraboloid is, this is a parabola. This is a paraboloid, and my goodness, the design looks pretty yabai. Sorry about that. So we'll make a huge circle here, and then we'll make some paraboloid here that didn't hit the straight line. Okay, so here is a paraboloid. Hopefully it doesn't give out any suggestive themes. Z equals to 4 minus x squared minus y squared. So this is 4. So the circle is at the xy plane. So this the area of x, the part where z is equal to 0, and then this axis xy exists. That is the xy plane. And then they say it wants to find the flux of the vector field. So the vector field is x cubed, y cubed, z cubed. That is the vector field. And then, and I believe that's it. Yeah, I believe that's it. That's all the data that we have. Yeah, so just so you guys know, this can also be used to calculate the flux, the flux of the vector field. So flux is kind of like, what do you call that, in electric field, I think. I can't really remember that. So anyways, F. So if we want to do this, we need to first find the divergence. Either way, you can either do the divergence first or set the regions first. Any way you like it. So I think we'll just do the region first. Okay, so since x squared plus y squared is equals to r squared, So this one we can convert this to 4 minus r squared. Now r squared, if we do that, so r squared equals to 4, but r is equals to 2. So now we have the regions. That means it would be 0. We'll start with z first. So z 4 minus r squared. And then for r, 0r would be approaching 2. And then the theta. So the theta would be 2 pi, 0 approaching 2 pi. So that will be the parameters for our question. So okay, the next thing we need to do is find the divergence of f. So the divergence of f is actually by getting x squared, x cubed, y cubed, and z cubed. Get the dot product of fx, fy, fz. So fx x cubed plus fy y cubed plus fz z cubed. It's not that. Z cubed. Okay. So now we have to do the partial derivative of all this. So it would be 3x squared plus 3y squared plus 3z squared. So now we can convert this further, since we're using these parameters. So x squared plus y squared, so this would be 3r squared plus 3, is it like 4 minus r squared? No, I don't think we need it. So we'll just do 3z squared. So now we'll put inside the formula of Q divergence F dV. Convert this. So now we can, there's a common factor of 3. Take this in, take this out. So 0 approaching 2 pi, then 0 approaching 2, and then 0 approaching 4 minus r squared. R squared plus z squared. So since this is a cylindrical components, I think it's cylindrical components, yes. So r dz dr d theta. We have to do the triple integral based on what is given here. So 3, 0, 2 pi 0, 2. So we'll immediately start to integrate z. So this would be r squared z plus z cubed over 3. No. Wait. We forgot the r again. So r 0 to pi 0 2 0 4 minus r squared. So this would be r cubed plus z squared, rz squared, dz dr d theta. This is just a bit of a mess here, but never mind. So 3, 0, 2 pi 0, 2, 0, 4 minus r squared Okay, not again. Wait. We'll do that again. So this would be R4 over 4 plus. Wait. Since it's Z, isn't it? So, okay. R cubed Z plus R Z cubed over 3 dr d theta approaching 0 to 4 minus R squared 3 0 to pi. This is gonna be a bit rough. But I think I'll leave the integral details to you because it's pretty long, kind of differential plus 4 minus R squared and then R over 3, and then there is dr d theta. So the part continues. There's still more to this, but since we have the Z cube here, it's going to be pretty difficult to actually solve all of this. So never mind, we'll move on to the next one. This will be the last exercise. So this would be Stokes Theorem. So Stokes Theorem, it's also a line integral f dr, but this time it's a double integral over the region R with this thing with the cross product of the vector field the A and the A. So and here is actually like the normal or something. So wait, we'll make this n bigger again. And the A. So remember, this is the curl. So we'll do some exercise here. So we'll get another exercise. Alright, so the vector field is like this, fx, y, z. This would be minus y x squared z cubed. But we need to find the curl. We should also find the curl. So the curl is the cross product of the gradient. So if we do like curl minus y x squared z, oh no, okay, just remember that if we remember the curl back again, one sec, it's curl is a vector form, fx Fy fz. This is gonna get pretty damn long. So Q. So we have evaluated this in a matrix form. So cross product is like it's in a matrix form. So I'm not going to go through that. Just remember we need to do the curl. So it's this minus this plus this minus this, and then this k here is this minus this. So if you guys do know how to do that, in the end we'll get 2x plus 1 k. So that will be the curl for the question. Oh yeah, I didn't show you guys the question, didn't I? So wait, okay, this is the vector field given. So here is the x, y, z. So it's like this, it's like that, and then we'll do an xy plane here, and then here is the line that we need to find from the in a closed surface. So that if we look from here, that would be counterclockwise. It's traverse counterclockwise. So okay, curl with the dot product of the normal vector. Okay, and then this plane is actually x plus z equals to 3. So if we want to do the normal vector, we need to do the partial derivative. So f x y z, this would be x plus z. But if we do the partial derivative, it would be like this, I think. F. So if we convert this to a vector form, this would be 1, this would be 0, this would be 1. And then we need to also find the magnitude. That is an awful way of drawing that. So f 1 squared plus 0 squared plus 1 squared. That is not how you draw the... Wait, that is the way how you draw the square root, but never mind. So that would be... the magnitude would be square root 2. So using these two data, we can get the normal vector, which is 1, 0, 1, and the magnitude is 1 square root 2, 1 over square root 2. It's like the normal vector. It's like a unit vector, but it's actually a normal. So you get the point. So we use this vector in order and put it inside this formula. So integrate from r. Oh yeah, and also this one would be x squared plus y squared equals to 4. So the r would be equals to 2. Now what we need to do is do the curl of, starting from the curl of this 0, 0 to x plus 1, and then the curl of this. Uh, 1, 0, 1. So since this is ds, not dA, sorry about that, 1 over 2, and then this would be square root 2 dA. Cross that out. So we'll do the dot product. This would be 0, this would be 0, this would be 2x plus 1. So now we have the, so since this is the region, it's a circle, so from 0 to 2, no, the circle, so we have to use polar coordinates from 0 to 2 pi, 0 to 2, 2x plus 1 r dr d theta. So that's it. That's for this. So we have to change the 2x plus 1 to x is equals to r cos theta. 0 to pi, that is an awful pi, 0 to 2r cos theta plus 1r plus 1r okay, 2r squared cos theta, 2r squared cos theta plus r dr d theta. So 0 to 2, and then 2 pi, so this would be 2r cubed over 3 cos theta plus r squared over 2, approaching 2, 0 approaching 2, 0 to pi. So so from 0, all of these are 0, so this would be 2r cubed, so 2 times 2 cubed, 2 times 8, 16, 16 over 3 cos theta plus, so 2 squared over 2, 4, 2, 2, so the theta. We're getting close to the answer. 0 to 2 pi, no, not 0 to 2 pi, 16 over 3 would be sine theta, so differentiate cos, cos will be negative sine, differentiate sine becomes cos, integrate cos, it becomes sine, 16 over 3 sine theta plus 2 theta, 2 approaching 2 pi equals 2, so it would be so from 0, all of this would be 0, so the answer is 2 pi, 4 pi. The answer is 4 pi. And the answer is correct. We have reached the end of today. We have reached the end of today's exercise, today's class. Well, it's not really class, it's just more like a study stream to revise whatever we've done. So anyways, let's go back. Let's go back. Alright, lads. I think it's time I start making. If you guys remember my marshmallow stream, where I read the marshmallows given from from you guys, so I think I'll read I'll read the marshmallows as of now. So hold on, yeah. Okay, we'll get a source. Browse that. Okay, wait. Give me a second. Alright, there it is. So, okay. This is the question that I actually overlooked during my marshmallow stream. There were 2 marshmallows. So okay. So when do you plan to get your own live 2D avatar? Live 2D avatar, I really shouldn't talk about getting live 2D avatar at the moment, because as of now I'm just thinking that I would actually just stick with the avatar I have right now, and if I get, and I might get a live 2D avatar after I actually do a lot of my activities, maybe in 6 months or a whole year, because because I am actually broke. I mean, which student isn't actually broke at the moment? But maybe if I could, I might make a live 2D of my own avatar here. Maybe I'll animate it myself, or get someone to rig it for me, because I mean, getting a live 2D avatar, I know it's really expensive at the moment, especially doing full body avatar. I haven't actually decided if I would rig it myself, rig this avatar by myself, or I would get a new avatar where someone made the avatar for me and animate it as well. So that yeah, maybe when do I plan to get my own live 2D avatar? At the moment, I haven't really at the moment, not at the moment. Maybe in somewhere around 6. It'll take me a while for me to get my own live 2D avatar. Okay. So not at the moment. Maybe in the near future, but it hasn't been decided yet. So okay, and then we'll do another. Here is another question. What's my main targets? My main targets are literally my goals, actually. So I'm just gonna stick doing with my activities for 6 months. I do aim on getting 1,000 subscribers, but 1,000 subscribers as of now seems out of reach, but it's okay. We'll see what the journey lies ahead. But also, I would also want, as of now, I would target myself to actually start doing some cover songs. Not at the moment, and in the near future. As of now, I'm just taking some vocal lessons on YouTube, because I can't afford a vocal coach. So I won't get a vocal coach, but I'll do vocal training like almost every day. And next week I plan to actually do a karaoke stream, but it's a cappella only, because doing so might because I don't understand the copyright at the moment, so I'll just stick with me using my dreadful vocals to sing through the songs that I like. And the songs that I like would be pretty much some old school songs. And old school songs. Like maybe songs that are from that are more than 5 years old, maybe in 2015 and below, I guess. So, but okay, my main target as of now is just to keep doing these activities, because I just think that I want to explore and find my niche, because as you guys probably know, there are a lot of VTubers out there, and you need to find a specific niche or a specific thing so that people can watch you for that kind of reason. Okay, so next week will be not really a pretty busy schedule, it's just a typical schedule. I would be try and venture into whatever I can actually do. Maybe do a bit of drawing, maybe do a bit of karaoke, and I'll play another game as well. So as of now, we'll just we'll just go through this journey and explore whatever we can do. Alright. Oh yeah, and as of now, my subscriber count is 18, which I got a very long way to go. So guys, if you enjoyed the content I make, leave a like, share it with your friends and family, and subscribe to my channel. That would actually help me a lot. So that's all from me, guys. Thank you for watching. Bye bye.